She's a science curriculum specialist, and we are so excited to host the first STEM Cafe in Oklahoma, period, here at Union High School. We partnered with the Tulsa Regional STEM Alliance. We hope to do this once a month. Perhaps we've outgrown our space already, so look for posters. And we're so excited that you guys are here. Hopefully we didn't run out of food, but now we know. Now we know the level of interest of STEM at Union High School, and we're so excited to see you guys. I'm going to introduce Emily Mortimer with the Tulsa Regional STEM Alliance, and she'll introduce our speaker.
So welcome. We are so excited to be here, and I have to admit, I had nightmares last night about nobody showing up since it was 7:30 on a Tuesday morning, but you guys have really proven that Union is all for STEM, and we appreciate that, and we are so excited about what this kind of program has here at Union. I do want to just do a quick introduction to a very, very interesting man. Dr. Diehl Teeters. He's a chair of chemistry at the University of Tulsa. He's been there about 33 years. And Dr. Teeters, he's an Oklahoma native. He actually has his roots in research, starting as an undergrad studying tumbleweeds. And yes, you heard me right. He's a chemistry person studying tumbleweeds, which is a plant, if you hadn't noticed. But it's a really interesting plant, and he has gone from there to hold the first patent in North America for nanotechnology and nano batteries. And today he's here to discuss with us some of his research, which includes almost 100 publications, including journal articles, conference proceedings, and books. So very accomplished, wonderful, beloved by all of his students and faculty members, Dr. Diehl Teeters.
Well, I'm so pleased to be your first speaker, and look at this crowd. Goodness, thanks so much. And I'd like to thank Union Public Schools and the STEM Alliance for putting this on and inviting me here together. I want to introduce a couple of people. I have Echo Adcock-Smith. She's one of our PhD students from the University of Tulsa, and John Ostrander. Echo is certainly interested in doing all kinds of volunteer work in STEM. And John actually, before he came back to get his PhD, was a teacher around this area, and so they might serve as a resource in case you have some questions. So you said I was beloved by all my students. You better ask Echo and John to make sure that they agree with that. Well, thank you again for inviting me, and today I want to talk a little bit about nanotechnology, and specifically what is nanotechnology and can it help us solve our energy problems. And so I feel like a weather person. I've never done this before. So what is nanotechnology? Well, if you look at the National Nanotechnology Initiative, the definition is the ability to understand, control, and manipulate matter on the individual atom and molecular level. And that's a quite amazing thing that 15 years ago we really couldn't have done. It's only probably been in the last 15 or 20 years that we have the technology to really appreciate and do nanotechnology. And the goal of nanotechnology is to create materials, devices, and systems with new properties that can benefit society in general. And the vision is the ability to control matter on the nanoscale, which will lead to an industrial revolution. We're already seeing some of that happening today. So how big is a nanometer? So a nanometer is 1/1000th of a meter. That's approximately, for us people in the United States, 1/100000th of a yard, approximately. It's approximately 1/50,000th the diameter of a human hair. Remember human hair, I'm going to come back to that later on. And a nanometer compared to a person is the same as comparing the size of a person to the orbit of the moon. And here are just some examples. So here's an ant, which is 5 million nanometers. A head of a pin, 1.5 million nanometers. A red blood cell, 750,000 nanometers across. And actually the diameter of a DNA molecule is 2.5 nanometers. So that gives you maybe some idea of the dimensions we're talking about. Yesterday's science fiction. How many of you in here have ever seen or heard of the movie Fantastic Voyage? Actually, more than I thought. Okay, let me tell you about the movie Fantastic Voyage. It came out in the 60s, I think in the late 60s, maybe 1968. Right? And let me tell you the premise of this movie. And so what happened is the President of the United States was involved in a serious accident, and a life-threatening accident. The old technology couldn't save his life, and of course they had to save his life. This was the period of time of the Cold War, And so they really had to do something, and they wanted to turn to a new technology in order to try to help the president. What they were going to do was they were going to shrink a submarine, and here's a submarine here. You see it's being shot at. Anyway, they shrank a submarine small enough, and the crew, so they could inject the submarine into the artery of the president. And then the submarine would wind its way through the arterial system to the place where this debilitating blood clot was, and use, I guess, a nano laser gun and get rid of the blood clot. Of course, it has all kinds of twists and turns. I'll tell you that there was a person on board the submarine who wanted to scuttle the mission. They're almost destroyed by various blood cells in the body. They're almost sucked out in the lungs because they had to stop one time and refill the submarine with oxygen. It's just a really campy movie, and I know you could download this on, Netflix and places like that. You might want to do it. Like I said, it's a 1968 movie, really campy. Shrink a submarine down, inject it to an artery, let it manipulate its way through the body, and save the life of the president. Of course, that's science fiction, isn't it? Science fiction, right? So I don't know. Let's think about it. So here are some of the things that nanotechnology will be involved in improving, such as coatings, powders, devices and microelectronics, energy and industrial sector and medical applications. And here are some of the numerous things that nanotechnology is proposed and actually is becoming involved in all the day. So nanotechnology is permeating the technology in our society today. So what's behind this great promise of nanotechnology? Well, really, I teach an advanced nanotechnology course, and you know the two things that really give nanotechnology its kick are it's the surface that you're dealing with, and it's the size. And I'll go into that a little bit. And it's, as I said, it's been only recently in the past 15 or 20 years that we really had the technology to see and manipulate atoms and molecules and understand the promise of nanotechnology. And so let's talk about it's the surface of nanotechnology. So nanoparticles, tiny little particles, are one of the main things that we focus on in nanotechnology. And what gives them the special property? Well, this says shells in a hexagonal close packed particle. Well, simply let's just say if you have a single atom and then you surround that atom with as many other atoms as you can, that's one shell, and then you surround that shell with as many atoms as you can again, and you just keep making the shell bigger and bigger, and that's what a hexagonal close packed system is. Hexagonal close packed basically as close as we can stack atoms. If we start with one, put a shell around it, as many as possible, put more about. That's called a hexagonal close packed system, and that's as many atoms as close packed as we can put them. And so here are the number of layers that you have, and this is the percentage of atoms on the surface. So when you have a big particle over here with 120 shells, lots and lots of shells, and you look at the percentage of atoms on the surface, it's really pretty small. But when you make the particles smaller, which means having less and less shells all the time, all of a sudden you get down here where you have 20 shells, and you see what happens is now I've got 20% of those atoms on the surface. And if you make the particle smaller and smaller all the time, you have 60% of the atoms in that particle on the surface. And it's surface atoms that give nanotechnology its properties, because surface atoms are different than the atoms that are in the bulk of a material. Surface atoms are exposed. Surface atoms behave differently. They have different chemical properties than atoms that are tucked in the bulk of the system. And so when you start making smaller and smaller things, and here's kind of gives you an idea of what sort of scale we're talking about, all of a sudden you have a lot more atoms on the surface that can do very interesting things. So that's one of the things. It's the size. It's a surface. And the other one is the size, and this is a little more difficult. I don't know, maybe some of you might have some quantum mechanics sometimes. Certainly if you come to, if you go to college and take physics and chemistry, you'll have quantum mechanics. And the fact of the matter is, when you get things that are small enough, all of a sudden the classical physics, which certainly you do study here, the classical physics doesn't work anymore. And special type of physics comes into play called quantum mechanics, and it's because the molecules, actually the nanoparticles we work with, are so small that all of a sudden a special type of physics comes into play. For instance, I'll ask you now, what color is gold?
Pink.
Gold, you're right. Well, I don't know. Maybe we ought to think about that. And here it is, gold. Let's think of the properties of gold. It's usually non-reactive. Gold's non-reactive, that's why we use it for jewelry. It's also gold colored, just like you told me. But let's think about gold nanoparticles in a slightly different way. So gold metal, usually not reactive, used for jewelry. It's golden color, and it melts at 1,947 degrees F. What about nanoparticles of gold? It turns out gold nanoparticles, when they're small enough, all of a sudden become very reactive. Why? Because it has so many of those surface atoms exposed. And remember, surface atoms are different. And they all of a sudden become very reactive. And gold, the color depends on the size. The smallest gold nanoparticles, 2 to 5 nanometers, are really yellow-orange in color. The mid-range particles, 10 to 20, are wine red in color. And the larger particles, 30 to 64 nanometers, are blue-green in color. And that's because that special physics, quantum mechanics applies. When things are that small, we have different properties. And then if you look at the melting properties, 5 nanometer diameter gold particles melt at 1536, 2 nanometers 662, and 1 nanometer gold particles melt at 392. A big change in the physical properties of these gold materials. So is nanotechnology new? Well, actually, nanotechnology has been around for a long time. We just didn't always know what was going on. As a matter of fact, stained glass windows, if you go to the stained glass windows in Europe, the ones that have this bright crimson red, how they were made was actually made by chemistry by making nanoparticles. It's just that the artisan didn't know they were working with nanoparticles. They just discovered that a certain type of chemical reaction created something bright red, and it never faded. It never faded. And so the bright red, I don't see a bright red there, there's some purple there, in stained glass windows in Europe, the old ones, were actually from gold nanoparticles in the system. And Mother Nature has done nanotechnology for a long, long time. It's called biomimicry, and we'll come back to that. So biological systems on the nanoscale. Excuse me. Bone, shell, surfaces, biomotors, biomembranes. Mother Nature is great at nanotechnology. And as a scientists and engineers, we want to try to figure out how to mimic Mother Nature because she is really something with using nanotechnology. And at the end, I have a video to show you that will maybe demonstrate that a little bit more. So let's look at some of the things Mother Nature do. Bone is one of the most important hard tissues in animals. It's really both rigid and hard, and that's a great property to have. It's hard, it gives us the strength to hold our body up, but it's also flexible enough that it's reasonably hard to break it. Yeah, you can break your arm, but it's really pretty tough to break bone. And what bone is made of is you have fibrils that are 100 nanometers in length. And these fibrils in bone are laid at 90 degrees to each other. And so I guess it was Mother Nature that first discovered something that we use a lot in construction, and that's plywood. Plywood is made from wood strips where the fibrils in the wood strips are laid at 90 degrees. Plywood is a great building material, has great properties, and maybe we got that from the way Mother Nature uses nanostructuring to make bone. Shells are also an amazing thing that Mother Nature has made. They're long admired for their beauty, scientists and engineers, because of their amazing physical properties they have because of their nanostructures. So what are they made of? It turns out that bones are made of blocks that are 500 nanometers thick and about 1,500 nanometers long. And then these blocks are stacked together like a brick wall. And the mortar between the brick wall, which is an organic matrix sort of stuff, which is kind of flexible, is 40 nanometers thick. So there's 40 nanometers between these bricks, if you will, and the organic mortar between them makes the bricks sort of flexible. And so what happens is that this the shell has an incredible fracture strength. And we're actually still trying to make materials that are like shells. If we could make materials similar to shells, we would seldom have chips and coatings, and I tell you, there's a lot of work going on trying to do this exact type of nanostructuring to make those materials. They would have amazing properties we could make them. This is actually an image that we took at the University of Tulsa, and this is the surface of a butterfly wing. Okay, and so I have a friend who has a collection of butterflies that another friend gave to him from South America. He's had that collection for about 25 years. And those butterflies are still bright and phosphorescent looking. And you know, if you had something that just had a natural dye, if you think about it, exposure to light tends to fade almost all natural dyes. Those butterflies, after 25 years, are still just the same color that they were, and beautiful. And how do they have their color? Well, this is the nanostructure that butterfly wings have. And butterfly wings have these ridges in them, very ordered ridges, which diffract light, and that's what gives butterfly wings the color that they have. And you can see there's more structures here. These are called braces. And I've looked around, I don't know what those braces are, but they brace this. But this actually acts as a diffraction grating, and that's why butterfly wings have that beautiful color that won't fade. Now what's interesting is, have you ever looked at the underside of a butterfly wing? Pretty dull, okay? Usually browns or something like that. Not phosphorescent at all. What's the underside of a butterfly wing look like? Still has the ridges, but they're farther apart, so they don't diffract light as well. I guess there's probably some biological advantage to that. Maybe from underneath the butterflies can't be seen, but from the top they can be seen to attract mates and things like that. So Mother Nature used that. And of course, here's Echo's arm. That's her arm there that she has, and that's her muscle. Okay. And muscle, which you'll certainly study about in your biology classes, is also a nanostructured material. You remember probably it's made of myosin, and these are proteins 30 nanometers long and 2.5 nanometers thick, and actin, niacin and actin. And then actin filaments are 160 nanometers long and 2.5 nanometers thick. And these niacin and actin systems actually move back and forth between each other like fingers going in like this. And that's what allows you to move your muscles. And that's a nanostructure that has properties that help us to move our body. And then cilia and flagella. Cilia are present in our lungs, and they're also present if you look at various bacteria and protozoa. And I think it's really great. You can see these in water. If you ever want to do this, there are kits that you can buy, and you actually have to make the water a little viscous so you can see the movement of their flagella, and they're just pretty interesting. And these are what are called motor proteins that they have, and this is a nanostructure. There's the actual motor and their central tubules, and I won't go into how it's made. I'm not sure I understand it. But either these allow the flagella to move like this because of the nanostructure that they have, and there's some that even have a rotor that spin around. Well, cells are the ultimate nanomachine, and I'll come back to that. But let's stop and think about how we work with nanotechnology. How do we see? Well, in the visible world, we use our eyes and cameras to see. In the nano world, we use scanning electron microscopes. Here's a scanning electron microscope we have at the University of Tulsa. We use atomic force microscopes, and here's a couple of atomic force microscopes. Near-field scanning optical microscopy, there's one of those systems we have, and scanning tunneling microscopy. We use those sorts of systems to see on the nanoscale, to see things and actually work with them. The building blocks. In the visible world, we use bricks and girders and 2x4s and shingles and sheets of metal and plastic. In the nano world, we use carbon nanotubes, nanoparticles, nanofilms, and we actually use molecules and biomolecules and manipulate those individually. This is a picture from some research we did at the University of Tulsa. These are actually carbon nanotubes. We did something really interesting. We actually put a tiny crystal of metal inside of that carbon nanotube. And we did that at the University of Tulsa, and we were quite proud, but I want to tell you something about the science that goes on. So we did that. We took many pictures of our system. It was a great thing. And we tried to reproduce that many, many times after that. And we've never been able to do that again. And we never know what happened. We don't know why it worked that one time, but it hasn't worked since then. So science sometimes has its mystery. Perhaps some of you can figure out why this happened and figure out how to do it in the future. So how do we build? In the visible world, we use hammers and saws and shovels and cranes, tractors and bulldozers. In the nano world, we use atomic force microscopes that can actually push molecules and atoms around. We use molecular self-assembly, where we get the molecules themselves to put themselves together to build automatically. We use electric fields and molecular tweezers to move molecules, to line them up and to make things. What do we build? Well, in the visible world, things that can be used in our society. In the nano world, new and maybe novel things that our society can use. And benefits of nanotechnology, well, in the future, quantum dots that help find disease, and Dr. Roberts, who ECHO works for, actually has done some work using quantum dots to try to find mutations in DNA molecules. Materials that have a fraction of the percent nanotubes have 30 times the strength. They're already using carbon nanotubes on the nanoscale in golf clubs, and they're also using in tennis rackets to improve their strength. Carbon nanotubes, they can make cables that have 200 times the tensile strength of steel but are so much lighter, and monitors with high resolution, and computers with 1,000 times or more the speed of those we have now. And the national support, well, with all this promise, and the promise now being fulfilled, really it started in the Clinton administration, it continued through the Bush administration, and it's continued through the Obama administration in funding for nanotechnology by the federal government. So, what is the timeline for commercialization? Here's this chart I showed you earlier. And so, medical diagnostics, composites, display, sensors, nanotechnology is already being used in those areas now. Energy, fuel cells, food packaging, biomaterials, drug use, lubricants, textiles, nanotechnology is always being used in that now. I'll give you an example of textile, and actually there's a company here in the area, I think it's in Broken Arrow, who sells socks and clothing that are impregnated with silver nanoparticles. Why would you do that? Well, it turns out that when you make silver small enough, remember you have a lot of atoms at the surface, it starts behaving differently, and all of a sudden silver nanoparticles are harmful to bacteria. And so if you put just a tiny bit, it doesn't take much, of these silver nanoparticles in the material, in the socks, all of a sudden they kill bacteria, and what happens? You don't have any smell on your socks. Now why are they selling this? Well, they sell this for people sometimes who hunt, because they don't want the animals that they hunt to smell them. And the socks impregnated with nanotechnology, with nano silver particles, actually don't smell. And so there's a company here that's actually doing that work already. Let's see what's next. And in the next 4 to 9 years, cosmetics and paints and this sort of thing like that, tissue organ and MEMS and smart implants and the rest. And then 10 plus years, quantum computing. I guess maybe there's already some quantum computers out there, and all kinds of things that we can expect in the future. So, nano batteries. Emily mentioned about my nano battery work, so I'll just mention a little bit about the nano batteries that we've made at the University of Tulsa. And so we've actually made some nano batteries, and we construct these, and we make we make layers of nano batteries about the size of a dime. Okay? And what we have tiny pores in a membrane, and we fill those pores with a polymer electrolyte material, and then we cap the particles, or these membranes with the holes. We cap the holes with anode particles, and here's some. And then the whole bottom is just a whole cathode material like this. So if you look at this area here, that is actually one individual battery. Okay? That is a battery. There's the anode, here's the cathode layer, here's the electrolyte, and that's what a battery is. And of course we all know what batteries are, but I think the trick to the work that we've been doing is, what's the size of our batteries? Well, here's a human hair, okay, and this box shows roughly the area that I've blown up with over here. And And beneath this is that membrane. I guess this works. Beneath this is this membrane here filled with all of these pores. And you can see those pores, the tops of all those pores now. And so we can fill those pores with electrolyte and then cap the top with an anode top and actually make each one of those pores into a battery. And so each one of those pores, if you look at the size of those, they're 200 nanometers across the top. And so here's the human hair, and you can barely see the edge. It's actually less than shown there. And so we can actually put 240 of these individual nano batteries in the diameter of a human hair. We can wire the nano batteries, and actually here are some nano wires, and so here's actually a copper wire that we run up to an individual nano battery, and here are some of the tops of the nano batteries, and we can wire the nano batteries with individual wires, and so we can do that. Now, what do you use that for? Well, when we make the nano batteries, we like to do fundamental studies on them so we can understand the fundamental properties of the materials that make batteries and help make better batteries. But there's some other reasons why we want to make nano batteries too. And this is one of them. Is nanotechnology science fiction? Remember Fantastic Voyage? Took a submarine, injected it into an artery, right? You remember that? Great science fiction movie. Camping, you should look at it, okay? So, but is that science fiction? Well, here's a company from Germany that actually has developed a tiny submarine, and here's a picture of this submarine in the artery of a human body. And guess what they propose to use that tiny submarine for? The same thing they propose to use it for in Fantastic Voyage. The submarine will propel itself through the artery, come to a place where there's a problem, probably a cancer, for instance, and eject some fluid, some drugs to take care of that cancer, to kill it. But it's so specific it can really handle the cancer cells. And this is what this company proposes, and that's the actual picture of their submarine. Okay? And so you got to remember, yesterday's science fiction may be today's science that we're working. And maybe, it'll be a University of Tulsa nano battery that'll power that submarine. Who knows? So I just want to talk about the cells. I want to finish. I have a little bit of time, it looks like. And let's see if I can figure out how to get this to play. If it doesn't, that's okay. So in a while, I hope the video will come up. We'll see. You think it will? It took a while on home last night, but that... Yeah, it just may not come up. We'll see if it does. Well, I know that you have to go at what, 8:15, I think. So we may not get this to work, but I'll certainly be glad to try to answer any questions over nanotechnology or any of the research we're doing. And again, I just want to thank you for having me. I'm so honored to be your first speaker.
Plenty of time for questions. We do have two quick introductions real fast. Natalie, also from the University of Tulsa. Would you like to make your quick announcement? Sure. She actually has a really great announcement about an event coming up that you guys just might be interested in. Something you may want to be able to speak to her after our event today.
Hi guys, like she said, I'm a student at the University of Tulsa. I'm not a graduate student, I'm an undergrad, and I'm a senior studying biochemistry. So if any of you are interested in biology or chemistry or biochem, I can help you out there if you have any questions, or just getting into the college process. Just a show of hands, are you guys all seniors, juniors? If you're a freshman, raise your hand. Sophomore? Nice. Juniors and seniors. Okay, a lot of seniors, that's great. Well, it doesn't matter, any year, freshman through senior, we are hosting a STEM fair for high school students. So this is just a fair that'll expose you guys to all of the disciplines in STEM, all of the organizations that we have on campus in the STEM fields, and we're gonna give free tours, we're gonna give free lunch. We're going to fly in a speaker from NASA. So she is the first female Hispanic flight director from NASA. She's going to give an amazing talk. She gives talks all over the country. So it's going to be really fascinating. We want everybody to come. And it's going to occur on Saturday, December 3rd. And it starts at 9 a.m. So it'll go till about 1:15. So it's not going to take up your whole day. But we'd love to have you guys come. I have a few flyers here I'm going to leave. You can take a picture of the flyer so you have the information. And if you're a senior, we're going to offer you guys an application fee waiver to the University of Tulsa if you have not done so already. Some of you are probably dragging your feet applying to colleges. This is a great opportunity to get that application in. And it's a great opportunity just to see the school and to talk to current students at the University of Tulsa. So if you have any questions, you can ask me or Dr. Teeters. And I just commend you guys for showing up here. I don't know how many of you it was for your free will or if it was extra credit, but either way, maybe your teachers can give you extra credit for coming to the STEM fair too. Wink, wink. But we hope you guys come. If you have any additional questions, again, you can talk to me afterwards. Or you can go to our Facebook page. It's TU STEM. I might write it up here too. And on that Facebook page, there's a Google form where you RSVP for the fair. We just want to try to get an idea of how many people are going to come. It's not required, but we'd really appreciate if you filled out that RSVP form so we know how many to expect. Okay, thank you guys. Thank you.
Now we have one other introduction. Dr. Dodd, would you like to introduce your guests?
Sure. Well, I just want to say on behalf of Union Public Schools, thank you, Dr. Teeters, for giving us your time this morning. And I want to introduce Stacy Romerman, who's a member of our school board and a parent. So wave, Stacy. And then I also want to give our community partners a moment to tell who they are and who they represent. Britt, do you want to start?
Britt Embry with Crafton Tull Architects and Engineers.
Susan Teeters with the Tulsa Glass Building School.
Anybody else? All right. Well, thank you again for this incredible event. We're the first in the state to offer a STEM cafe, and I want to give props to both Ms. Gaines and Ms. Lim because if not for their initiative, we wouldn't be the first to host. So I'm grateful that our teachers are always looking for opportunities to